Okay, so now let's start with the last presentation of this session. So it will be given by Gleb Fiadziushkin from RWTH Aachen team, and he will talk about detailed investigations of resistive switching device fabrication process based on MOCVD 2D molybdenum disulfide.
Yep.
Okay, so please, the stage is yours.
Okay, good afternoon, everyone. My name is Gleb Fiadziushkin, and yeah, as Regina already said, I'll be talking about fabrication process of resistance switching devices based on MOCVD 2D-MoS2. So, as you all know, we are currently experiencing a rise in the number of AI applications. However, as you have heard a couple of times during this conference already, the underlying hardware is not well fitted for the task, at least the one that we are currently using. And the reason for that is the memory wall, or von Neumann bottleneck, if you would like to call it this way. And this is due to the physical separation of the compute and memory units from each other. And one way of addressing it is actually using the crossbar structures, which combine both the memory and compute functionalities in the same units. And these structures are optimally suited for matrix spectrum multiplications. And in the following talk, I will narrow it down to individual cross points. And here is just a small overview of the functionality of these devices. So typically, we require them to be able to switch between at least two distinct resistive states. And the physical structure is actually rather simple. So we have two metal electrodes, one on the bottom, the other one on the top, and the resistance switching material in between, which is actually responsible for this functionality. And so during this talk, I will first start by shortly introducing two-dimensional materials and MOS2 in particular. Then I will present you an exemplary fabrication route of such resistive switching devices, followed by some challenges that we can encounter throughout the fabrication and ways of addressing them. Finally, there will be a couple of short slides about electrical performance, and I'll provide a summary and outlook. So, when we speak about two-dimensional materials, you can imagine them as Lego building bricks, which are individual ones, basically 1, 2, 3 atoms thin, and you can stack them in completely different combinations. And this is all enabled by vastly anisotropic properties of these materials in and out of plane, to which I will not go right now into a lot of detail. Instead, I will shortly explain how we actually deposit these materials. For that, we use an already established commercial technology called metal-organic chemical vapor deposition, or for short MOCVD. And in our case, we grow the materials on 2-inch sapphire substrates, which can, in theory, also be done on 100-millimeter wafers. And this technology provides a clear pathway all the way up to 300 millimeters. And we think that these materials are, in particular, very interesting in case if you would think of implementing a vertical stack that consists exclusively of 2D materials, because then you would get a really big advantage in terms of the vertical thickness or vertical scaling. So with that, I would now move on to the hardware part. So how those devices are typically fabricated. Here I will not be distinguishing between the optical and e-beam lithography process samples, so basically the ones that are quite large and the ones that are small or scaled ones. So the fabrication starts by preparing a target substrate, which is in this case actually a silicon oxide silicon substrate. You can see on the top the top view and on the bottom the cross-section view. We next continue by depositing the bottom electrodes, which is followed by the transfer of the 2D materials. So as I said, we grow them on sapphire. The target substrate is different, so we have to mechanically take them and transfer to the other substrate, which is then followed by the removal of the excess of 2D materials outside of the functional area, which is finished by the top electrode deposition. So, it all sounds rather simple. However, we have a really big challenge, which is the mechanical stability of the two-dimensional materials. And in this work, I will be coming back to the same term several times, which is scanning electron microscopy. So this is a technique with which we are able to inspect these materials throughout the fabrication and actually control two types of common defects on which I will be focusing throughout this talk, which are tears and contaminations introduced throughout the process. And so let's now continue with the first step, which is the fabrication of the bottom electrodes. For these slides, you see also on the top right an overview, just for you to more easily keep track of the fabrication processes. And when we talk about the bottom electrode fabrication, we should always keep in our mind that as a next step, we will be transferring these atomically thin layers on top. So we want the electrodes to be as smooth as possible to prevent any excessive mechanical stress in the 2D materials as a result. So in our case, we have come up with a combination of an E-beam evaporation process and a liftoff. And in case if you do not see, for example, in your materials, if you're working with them, any large-scale defects after the transfer, it's still a worthwhile thing to take a closer look at them in case if you still have some issues with the yield, because at the edges of the metal electrodes, we have the highest amount of mechanical stress. So there you might get formation of very small pinholes. You can see from the scales, they can be 10 nanometers small, which can as well really kill the yield of your devices. So there are two approaches. The first one, quite straightforward. You can think of just transferring the second layer on top and hoping for the pinholes not to overlap. Here we'll be focusing on the other one, which is related actually to optimizing the transfer of the materials itself. So they have already mentioned a couple of times, we cannot, unfortunately, at the current point of time, deposit these materials with some scalable technique on the target substrate where we already have the bottom electrodes pre-patterned. So it necessitates this exercise where we mechanically transfer the material from one substrate to another. And as many other groups that work on two-dimensional materials, we actually initially started by using wet processes, where you basically have to dip your growth substrates into some alkali solutions, and as a result, the films are exposed to really aggressive chemical solutions and a fair amount of mechanical stress. So we moved on over time to a dry transfer process, which actually mitigates those issues. And you can see, for example, from the results, here you can see quite a bit of wrinkles. This one is very smooth, very nice, and also at the same time, it helps to eliminate these weak points that lead to creation of pinholes. So then the next point, which is also quite a bit of a headache, are actually the contaminations throughout the fabrication process. They happen because throughout the fabrication, we expose the materials to a myriad of other different materials that are required for fabrication, for patterning steps, and so on. So this would not be also bad if you were able to remove them. But this is not possible in case of 2D materials, at least at the current point of time, because you would typically also remove the 2D materials together with them. What makes the matter worse is actually that these residuals can be continuous. And one of the common steps where it actually happens is the patterning step, where the protective layer with which we cover the area where we would like the material to stay actually leaves continuous residues, as you can see on the right. So here you would basically have to carefully find a combination of the materials that would fit your two-dimensional material in order to end up with this nice, clean result. Now, let's move on to the last fabrication step, which is actually top electrode deposition. So I will split it in two parts. First one is about the lithography. itself. So if you have up till now ensured that the two-dimensional materials are clean, they don't have any defects, then what is the logical step before doing the top electrode deposition is maybe check it again. And this is possible again with scanning electron microscopy. In case of large structures, for the small ones, we cannot do it due to some certain reasons. And one way to address it is actually introduction of additional reference structures for the electrical measurements. So one such structure is actually does not feature any two-dimensional material in between the electrodes. So with this structure, you would be able to check, for example, for some mechanical defects in your electrodes after the fabrication, and also for the presence of parasitic species that we do not expect for successful fabrication. So basically, if your devices suddenly show anything different except for the ohmic characteristics, then it means that there was somewhere throughout the fabrication a mistake. And last challenge is actually the deposition itself of the metals on the two-dimensional materials. So for the devices that we have been fabricating initially, we very frequently observed that they were all just stuck in a permanent low resistive state, so they basically were shorted. And after optimizing the metal deposition process, so basically reducing the kinetic energy of the incoming metal species, we were able to reduce the damage to the two-dimensional materials, which actually has resulted in functioning devices. And this is not an insulated issue, so the field of two-dimensional materials has been working on these issues also in context of field effect transistors, for example, where metal deposition is still an open topic, and it very frequently results in the damages as shown on the following illustration. So let's right now summarize it shortly. So if you have some mechanical defects, what they will result in is short circuit between the bottom and top electrodes, basically destroying the functionality of these resistance switching devices. And the second point is that we would like to avoid the contaminations because we cannot have any processes that would remove them without destroying the material themselves. And I think I have been successful in convincing you that scanning electron microscopy is a very good technique to do the inline inspection. And with that, let's now move on to the results of the fabrication. So we have fabricated in this work a total of 4 chips, 3 with optical lithography featuring rather large structures, 1 with electron beam lithography. All of the samples have had nominally identical stacks for the bottom electrodes, for the 2D material, and for the top electrodes. And as a yield criteria, we have required from our devices to show at least one full switch and cycle with a difference in resistance of at least 1 order of magnitude. So, coming to the electrical data, as you can see from these following 2 plots, actually all of our devices show forming-free, non-volatile bipolar resistive switching. And when we talk about the yields, I will be here mainly focusing on these 3 points which are coming from the optical fabrication steps. We have quite good yields for a rather large number of devices. And what is more important is actually that the distributions for the set and reset voltages between these 3 separate chips are actually very close to each other. And yeah, with that, let's now take a step back and summarize. So we have established a fabrication protocol and also ways of controlling the devices throughout the fabrication, which provides us a good foundation for investigation of the 2D materials. So with that, we can move on to an interesting part, which is actually the science, where we would investigate different two-dimensional materials, try to tune them and see how do they switch, why do they switch, and how we can affect the properties in order to hopefully eventually be able to optimize these materials and the device structures to the specific applications. With that, I would like to acknowledge the funding agencies and colleagues from the Institute for Semiconducting Technology at RWTH for access and training to the e-beam writer, and you for your attention.
Okay. Yeah, thanks a lot. So there's time for questions. So while people are thinking about questions, I didn't catch, what are the electrode materials, or was it a secret?
It's not a secret. We were using palladium and aluminum. So palladium at the bottom and aluminum at the top.
What?
Palladium, PD.
Palladium,
Yeah.
okay. And aluminium as top electrode?
Yeah.
Okay.
So PD and aluminum. Yeah.
Okay, and what do you think is the switching mechanism?
That's actually a very open discussion still. The field, I think, solely converges on the idea that it's a filamentary switching type.
Yeah, this
in
is
the
clear from the
two-dimensional
curves, but what makes the filament?
Actually, I think in this case that would be aluminum atoms.
Okay.
Because it's more mobile than palladium.
Okay. Yeah.
And from some electrical data, we see some hints that we also have filamentary switching type in these devices.
Okay. Yeah. So further questions.
Perhaps I can ask my question. Okay.
Yeah.
So thank you for your talk. Very interesting. Have you checked the crystallinity since you grow, when I understand it well, with CVD, and then you transfer it to the sample?
Mm-hmm.
Have you checked the growth, and is this the stoichiometry and the crystallographic structure from the growth sample? And is it possible to grow directly on the sample?
So with regards to crystallinity, this is something that we are still working on. So these samples are typically polycrystalline. So when they grow as individual domains that during the coalescence form a lot of grain boundaries, for example. So we're not talking about single crystals here, definitely not on the wafer scale, since domains are usually of the size of several hundred nanometers in the best case. And then, what was the second part of the question?
Stoichiometry, if you have really, you say you have MOS2.
Yeah. Stoichiometry. We have been doing quite a bit of tests with XPS, and we are very close to this 1-to ratio. It's within like 5%. And I think there was one more, right?
Yeah, it is also possible to grow directly.
At
Palladium, for example.
So let's say currently I have not seen any experiments with MOCVD that would allow it. There are some different methods how you would be able to do it by, for example, depositing elemental molybdenum and then trying to sulfurize it by thermally assisted conversion. But this is not, this has not been done yet in commercial reactors. So in this work, we actually are focusing on doing these prototypes with the technologies that have a clear pathway. But this is something definitely that we are looking forward to exploring as well, because that would eliminate this transfer step in between. Thank you for your question.
Yeah.
Now, continue this question about the stoichiometry, because you said 5% is not too much. So in some semiconductors, you need a PM to change the electron conductivity. So you say 5% is not too much, is too less?
I would say we just at this point I cannot give you a good answer because we don't have enough data yet from these types of devices.
The second question is here from the images.
Yeah.
It seems that the interfaces you have some much lighter edges. Is that some artificial?
It's just from the SEM. So when you're doing the electron microscopy, just from the edges, from the side walls, you get like slightly different signals because the incoming electrons get reflected, and it's just an image artifact.
There is no partial oxidation from the
Sorry?
partial oxidation of aluminum.
It could be happening on the surface? This is actually a very good question. That's why we also have some reference structures where we have just aluminum and palladium touching each other, and we make sure that there is no oxidation and there is no parasitic resistive switching happening. Thank you.
Okay, are there further questions? If this is not the case, I would like to conclude the session, thank all speakers, and invite you all to our poster session and the coffee. So, see you tomorrow.